starts, okay, good. Okay, once more with feeling. So, this is the situation with oscillations. When you've got an energy level E, and it's just the way you imagine something rolling back and forth in a bowl. Okay. So what we did next was I'll do some numbering here. What we did next was we were looking at these U of X constant times magnitude x to the nth power, because this one was symmetric about the origin, and it's a potential well. And what you can do here, if you let E equal B times A to the n, then you're out here between A and minus A, stands for amplitude, right? And same discussion as before, but this time we can set this one up. So we'll do the quadrature, and we will take 1/2 m dx dt squared plus u of x equals e, and we'll separate variables again. And yeah, this is going to turn into a homework problem. So we will have dx dt 2 over m e minus u x got the square root. Then we do the separation of variables, and we have dt, got the dx 2 over m e minus u of x. And you know, I'm going to do this right here. So there's the time. We're going to work with this again. But what we do to turn this into the period of the oscillation, actually let's go ahead and do this. To turn this into the period of oscillation, we're going to integrate from minus A to A, and we're going to multiply by 2, because that's back and forth again. Okay. So we have that, and because we have a symmetric potential, we're actually going to go ahead and say 4 0 to A dx 2 over m e minus u of x. And then we're gonna go ahead and plug these things in here and get that dimensionless integral we had before. Okay. So this is all a review, but when you turn in this assignment, you're actually going to want to take it from the top. You're going to want to take it from here and turn in all these steps as well. So I'll show you where we're headed with this thing. So that was the, okay, so that's done. So what do we have here? T equals, we've got a 4, and we're going to pull out the root 2 over m here. In the integral, well, I'll go ahead and put it under the integral. 0 to a. We're going to have dx. Now the 2 over m's out already. We have the b a to the n minus b x to the n. And since we've done this before, we'll do a couple of things at the same time. We're going to get the b out. Okay. We're going to have 4 m over root m over root 2. We'll have the 1 over root b. We'll have a to the n over 2, and because point we have 0 to 1 dy root 1 minus y to the n. So we're going to clean this thing up and make sure this is what we had last time. T 2, I could go ahead and write 8 m over b, and then I'm going to have amplitude 1 minus n over 2 integral 0 to 1. Good. And this is the one we're going to work with. Y to n power. So that's the period of oscillations for this power law of a potential. And it was a pretty rich result. One thing we had last time, or it was last week, when n is equal to 2, 1 minus 1 is equal to 0. When n is equal to 2, we have the amplitude independence of the oscillations. Once we get there, we're going to study that for the next half of the semester. But for the moment, we have amplitude dependence depending on that power there. And what about this integral? For a couple values of n, we can get it in closed form, pi times something or other. Okay, but point is, this integral is just a number. Just a number. So all of the physics is actually out front right here. So you guys are going to turn this in, and what we're going to check though is the limit as n goes to infinity. That's the interesting one that I mentioned at the end of class last week. Right? So the limit as n goes to infinity, you clearly can't just plug infinity into here. Right? We have to do something else. And you can't plug infinity into here either. However, so let's go ahead and do homework. Find limit of this period. I could give it a subscript n as well, as n goes to infinity. That's what we're going to try to do. And before we consider this integral here, we'll once again look at these potentials that I had on the board a minute ago. This time, we have these symmetric potentials. As n gets larger and larger, they become flatter and flatter. So in the limit as n goes to infinity, that's what I mentioned the other day, you're essentially looking at a square well potential as n goes to infinity. All those lines aren't quite lining up. But here's what we want. We have energy and the amplitude A, and it's always U of A is equal to B A to the N is equal to E A. This is going to be the key to this problem, because we can use this relation in here before we take the limit. Okay? We can use that relation before we take the limit, and that'll take care of the problems in front of the integral. Okay? So that's the tip on this one. Now what about this integral as n goes to infinity? We're looking at an integrand that I'm going to do the simple version of this. Okay, so this was the potential, this is the energy, you're going to take care of that. If we're looking at that integrand, what function are we looking at? 1 over root 1 minus y to the n between 0 and 1. Okay. And so when y is equal, oh, sorry, that's not the x-axis anymore. That's the y-axis, okay. So when y is equal to 0, what do we have?
Not really anything. Infinity, I suppose.
No, y is equal to 0, not yet 1.
Sorry, when y is
1
equal
over,
to 0,
yeah,
and n is
1
0.
over 1. Right. When y is equal to 0, it's just 1. And the question is, what does this function do? The larger n is, the flatter this thing is, okay? So, you should play around with the calculator sometime too, if you want. As long as y is less than 1 nth power, you know, it gets suppressed a lot. It's only as y approaches 1, actually I shouldn't draw the 0 there. It's only as y approaches 1 that this thing noticeably increases. Now, like you were saying, when y is equal to 1, this thing diverges to infinity. So what this function looks like is this. And the question is, as n goes to infinity, is this little section get suppressed sufficiently? Because if it does, we can say this integral is just 1 from 0 out to 1. The integral itself will just be equal to 1. And the proof of that is interesting. That's kind of technical. So we're just gonna, you can play around with it if you want, but you can also just say, use limit n goes to infinity, integral 0 to 1, dy root 1 minus y to the n equals 1. That's a true statement. It's an interesting limit to take. If you guys want to spend a little time on that, you're welcome to. But you can just use this. And what we're then going to find is that this limit has a very basic physical meaning. Because if you're in a square well potential, it's force-free except when it bounces off the walls. So we should find something that's consistent with, find that V naught times T, and that's the T I'm talking about right here, is equal to, you know, where are we here? 2A times 2. V naught times T should be equal to 4 times A. In which case, that's a free particle that's bouncing off a rigid wall back and forth. So to get that out of this original calculation is actually a pretty nice and impressive result.
You want us to do that for the homework?
That's for the homework, yeah. But for the homework, I do want you to take it from the top on this, just so you go through these steps I just did and really get to know them. Okay. Turning that problem into a dimensionless integral where all the physics is out front, that's a good one. Okay. So that's the discussion of the oscillations in general. You can now say, generally speaking, these oscillations are amplitude dependent. Just as this one is clearly amplitude independent, right? The one that's just bouncing back and forth. And that allows us to go back to the case where n equals 2, where they're amplitude independent, and that'll be a major topic for quite a while now. Harmonic oscillation. But yeah, before you do the harmonic oscillations, I'd like to see other ones. You know, another interesting oscillation would be a bouncing ball. If you had an ideally bouncing ball that never loses amplitude, that would clearly count as an oscillation, right? What would that potential look like for a bouncing ball? And what would the graph of the position versus time look like? Remember, that's free fall, so that's something we really know well. Let me mention that briefly before we go on. We can actually keep some of this on the board of the bouncing ball. So I'm gonna go ahead and erase this. So everybody has this, right? That's homework assignment. Good. top. And that's really just the law of free fall. So if we have x of t and we drop it from a height, excuse me, we drop it from a height h from rest, what does the graph look like? Drop the ball from rest. We have, to begin with, we have x equals h minus 1/2 g t squared. That's for the first bounce. So it's just this downward parabola. Of course, it doesn't keep going, it bounces, but if it bounces ideally, it's just reversing. It's just reversing its velocity, right? So it's gonna do that. Make sense? That is something that's been launched with the same speed that it had achieved, going up and down. So that's the graph of your bouncing ball oscillator. Clearly not harmonic. And that infinitely sudden reversal of velocity is represented right there. You had a negative slope, that means it was falling down. Suddenly you switch to a positive slope, that means it's going up. So that would also have a period. It's not covered, strictly speaking, in here, but we can construct it simply from our understanding of free fall. The period of oscillations and all we can construct. Question is, what would the potential energy look like for the bouncing ball? Potential energy function. So we would have u of x. X is the vertical axis. Whenever x is 0, well, on the ponder. So you could be thinking u of x is equal to mgx, because that's the potential energy. That's the potential energy. But how do we get the bounce out of it? What we have to have is some very, very steep function with a negative slope. Okay? And as that function gets steeper and steeper and steeper, it's more and more of a sharp bounce. So, but if you take an example where it's not infinitely steep, but enough that you can see it here, that would be like the elastic bounce there. Then you see what you're actually looking at is something, with a local potential well. So that's how you would create a potential energy with a bounce. You would have to add plus, I'm just gonna write plus question mark here. You'd have to add something here that gives you a potential well. And then you're not so far from these ideas here. Okay, we'll leave this up. This isn't bad at all. Okay. You guys see what we have here? We have a negative slope. That's when the ball squeezes. So this is actually an elastic potential right there. The ball is squeezing and it's going to rebound. But it's just a very tiny thickness, whereas this is when it's free falling in the air. Okay, good. So now we're going to do the derivation for the harmonic oscillation. Once again, we're looking for that n equals 2, and we'll find it. I'm going to erase all this now. Okay, well, this is enough motivation for general u of x with a local minimum. So generally speaking, we have some function u of x, and it has a local minimum here at x of 0. Even on this graph that I just erased, that bouncing ball, it would have actually had a local minimum right down there in the crotch of the curve. But what we do here is expand in a Taylor series. You got a function, you got a local minimum, expand in this form, u of x naught, u prime, x minus x naught. And we need a couple more of these derivatives. And I'm just going to go ahead and put the third derivative and then say, and so forth, x minus x naught u plus and so on. Okay. So that's your Taylor expansion. And as we've been studying, we now go back to this graph. This is u of x naught. This value right there. The slope is 0 at a local minimum, therefore the first derivative vanishes. Because this is just some arbitrary constant, we don't have to really worry about it. So we can declare it to be 0, and we'll have u of x equal, I'm going to do something a little different this time, 1/2 u double prime. So this one I'm just going to write here, ignore, do that. X naught, I'm going to, x minus x naught squared. And I'm going to factor out, this would have been a 3 factorial, right? So if I factor out, what's my next term here? This is times 1 plus u third derivative of x naught over 3 u second derivative of x naught. And we're assuming that this is, strictly positive, non-zero, times x minus x naught, plus higher orders. So what we have to do is make this small. What we want to do is make this small enough to be able to ignore, and that means this has to be much less than 1. And to make this thing much less than 1, we say, well, we have control over it. It's a well-behaved function. We have control over it just by making x minus x naught as small as we need it. Okay. And that's what the definition of small oscillations is. And for the mathematicians, they might even take that as, infinitesimally small, and the limit is x minus x naught goes to 0. But for us, it just has to be small enough to make this expression much less than 1. So that's why I'll put under here much less than 1. And what do we have downstream here? We have even higher orders of x minus x naught. So those are safe, right? If x minus x naught is small, x minus x naught squared, much smaller. So there's our criterion. We have to make everything downstream here much, much less than 1 after we've factored this out. Then we can say let k equal u double prime of x naught. And that's how we get our 1/2 k x squared potential energy. Okay. So with this, now u of x equals 1/2 kx squared, and that's the one you always learned about that the spring would have, right? The spring constant. But the spring constant really means the second derivative of the potential energy function. I have a nice example to illustrate that goes along with what we had just talked about. Just on the board. So, good. So that's where the ideal spring comes from. Now let's imagine we have a real metal spring that's as ideal as we can make it, works really well. And see how it fits into this schema here. So for this example, let's do the following. We can erase this. Erase this and leave up that result. So this is a more real life example. What we're going to do is we're going to stack two pictures on top of each other. So this one here, we've got our ideal spring, and we'll hook a mass up to it. That's what we're going to do. On the x-axis, and this is going to be the u of x function that goes with it. So we have to declare a place where the equilibrium is. So I'm going to go ahead and put my origin right here. Before I could have called that my x naught, right? Could have called that the x naught, but I'll call it the origin. That'll work. So what does this function look like when this block is right here? If I've slid this over to the origin, in fact, since I got this finite width of the block, I'm going to actually make it this way. I slid it down to here. So this is where it was relaxed. And I started to stretch it. Yeah, this is our function here, 1/2 kx squared. So yeah, this is just gonna go like this as I pull the thing to the right, 1/2 kx squared. Okay. As I compress the spring, it's also gonna do this. So there's a regime throughout which this spring is ideal. And that's what the red part is here. But this is a real spring and this is a real wall. So once I press the coils all up against each other, what happens? And I keep pushing. It's going to take enormous force. And in fact, what am I going to do? Crush the atoms into each other? So as I come up against the metal itself and push into it, I'm naturally getting a diverging function here. That's no longer x squared. And if I stretch it too far, what's going to happen? I'm going to straighten it out. It's going to do funny stuff. As I stretch it too far, it's going to leave here, and eventually it's going to snap. Right? So even my ideal spring, my metal spring that I pulled off the shelf, has a regime of being ideal right down here. Here I stretch it, it breaks. Here I try to compress it, and I can't get it there. So it's this part here in red that we just had in our Taylor expansion. So the red part here, well, let's write red, u equals 1/2 x squared, and then up here, no longer x squared, and the same here. No longer x squared at all. So if we had a function like this, we could locate a regime in which it's actually x squared behavior. And I'm going to put together a whole raft of little examples of that type that we can do discrete cases. In fact, this one is gonna come back to see this one later on. What if I have a u of x equals, this is a total classic, a over x squared minus b over x. A, b, and x are all positive. When we study gravity, we're gonna run into this one again. But right now, I'm on the positive x-axis. I've got a over x squared, so you guys are thinking it does something like that. Minus b over x, we've been studying, basically does something like that. Okay. So how they add up isn't clear until you give it a little extra thought as to which one dominates and which limit. But what you find is this function, okay? And this function is exactly this. It has a local minimum, and we can expand it in a Taylor expansion. And what we'll get is small oscillations about that, okay? No, I'm gonna put this as a homework right now. This will be a good one. So for this example, here's our function, a, b, positive, x positive as well. Find x naught such that u prime of x naught equals 0. It's the first derivative criterion, comma, then u double prime of that particular x naught. And that's going to be the k for this particular potential. And we can do all kinds of examples like this. Turns out this is something from the theory of gravity, but right now, it's a perfect potential of the minimum. Okay, good. So now we have to get to the actual harmonic oscillations. We're going to repeat that quadrature example again. So let's call this harmonic oscillations. And this will be the n equals 2 from that prior discussion. So what we had when we did the quadrature was t was going to be plus or minus integral dx prime 2 over m e minus u of x to the 1/2. Okay. But now we have the example of e equals 1/2 k a squared and u of x equals 1/2 k x squared, because we've been doing these harmonic oscillations. We've been expanding these potentials, and so when we plug that in, we have plus minus integral dx prime, the x with the number found right here. So what do we have? The 2 over m and the 1/2 k, we end up with root k over m a squared minus x squared square root. But this time, this is an integral we can do. Upper boundary, I'll leave this one empty for now. So this one we're also going to do as a homework. trig substitution, and I'm just gonna say homework, show that with omega being defined as the square root of k over m, x of t can be written as a cosine omega t plus, I'll just say alpha for now, so this is just a constant. And see, chop chop, this is a familiar expression you guys have seen before. And generally you haven't seen it derived in this manner yet. We're going to derive it in a couple different ways, but if you do it in this way, what you can already see is that this root k over m, which is omega, you can pull it out and cross multiply over here. So you have an omega t. You have omega t equals this. Then if you do a trig substitution and choose the minus sign here, you get the inverse cosine. You choose a plus sign, you get an inverse sign. You use a minus sign, you get an inverse cosine. So this is really just filling in a couple of steps to see, so that you really see what's going on there. So yeah, once again, you've got the omega t right here, the root k over m, so you got omega t on the left side, and you do a trig substitution. Let I'll just write that, because it's just a couple steps really. You just verify that, but that really is the inverse cosine. Okay, that's the inverse cosine. So I'll just put here trig substitution. And then when we get to Newton's law again, this of course will solve Newton's law for the harmonic oscillator as well. So we'll get it in both ways. But yeah, we definitely wanted to get it from the general theory of oscillations first. Yeah, good. Okay, I'll just write it out what you. So you're going to have this omega t equals plus minus dx prime root a squared minus x squared. And you can let omega t equal theta to it. Let omega t, let theta to omega t. And then you'll see the trig substitution right there. Inverse cosine. Good. So that takes us to our harmonic oscillations. And a couple of things we can study on these. Let's see if we have anything to do about here. Anybody remember the differential equation we had for harmonic oscillations? I think we all do. So I'm just going to put this here so it stays on the board. Omega t plus alpha omega root k over m. So we can also approach this in the following way. Suppose we have m d squared x dt squared equals f. In this case, say it's minus du dx. So m d squared x dt squared. And I'll keep going here. Minus d dx of 1/2 kx squared. Because you see where this is going. this gives us the minus kx. And that gives us the minus kx. We have d squared x dt squared equals minus k over mx. I'll put a box around it. This is the one you guys have probably seen in Physics 4a for harmonic oscillations. So we're right there as well. And then if you take two derivatives of this thing, what will you find? So x d squared x dt squared d squared dt squared of what we have up there, a cos omega t plus alpha. So if you take those two derivatives, you bring out a minus, minus sign and then cos again, you bring out a minus omega squared equals minus omega squared a cos omega t plus alpha equals minus omega squared x. And what's omega squared? I have it up there, yeah. Omega squared is k over m. So yeah, that's the way we go through it in Physics 4a. And we'll have plenty of time to repeat this thing. But we wanted to see it happen through the quadrature, right? Through the definition of the separation of variables and all that. Okay, good. That's enough for now. How many problems do we have for next week? 2 or 3?
We have.
For this
3.
Friday, I mean?
We have 3 for 1 and 5.
Good. We'll have one on Wednesday and we'll have a good one for Lisa.